Sweet. Oh, all right. It's Thursday, everybody. Checking in, checking in. Cool. If you got questions before we begin, let me know. There we go. Got some more people. Oh, where's me? There's me. Cool. Okay. Again, if you got questions, ask away. And if not, we can start the lecture. And let me find business math. And here are the notes we're covering today. There we go. So if you need to download them and follow along, let's do it. Where's all my cloths? Each one. There's my gray one. Okay, cool. All right. If you just came in, I'll post the notes again in the chat. This is what we're covering today. 5.1 and 5.2, linear inequalities in two variables. All right, so let's get started. Okay. So for 5.1, we have linear inequalities in two variables. This describes a half plane when graphed. Use the following steps to graph a linear inequality in two variables. So use the inequality to write a linear equation, which serves as a boundary for the graph. So whenever we're given the linear equation or the inequality, we're going to change the symbol to equals and either graph the equation by slope-intercept form or use the X and Y intercepts. 2, if the original inequality has an equal sign, such as less than or equal to or greater than or equal to, then when we graph the line, it will be a solid line. If we have just a less than or greater than, this means our line will be dashed. Okay, so it's going to be important when we start graphing them. And then after we graph our line, our equation, we're going to want to pick a test point above or below the line. And we're going to plug that into the original inequality. And if it holds true, we will shade on the side of the point we chose And if it's false, we will shade on the opposite side of the point that we have chosen. And of course, I'll work through all of that in these examples. Okay. So first up is y greater than x plus 1. Okay. So I'll just zoom in real fast. So our first step, like we said, is to change this to y equal to x plus 1. So all we do is change it to equals. We already did matrices on Tuesday. Okay. So now here we're going to use the X-intercept and Y-intercept method. So this is the method we are preferably going to choose when graphing these linear inequalities. So when we look for an X-intercept, remember that X-intercepts are on the X-axis. So whenever you look for an X-intercept, you let Y equal 0. So we'll just plug that into the equation above, and we'll get 0 equal 2x plus 1. And we have to solve for x. Move that negative 1 over, and we get x equals negative 1. Okay, and this becomes a point, negative 1, 0. All right, and then we want to find the y-intercept. And y-intercepts lie on the y-axis where x is 0. So to find a y-intercept, you let x equals 0. And we'll use that equation from above. You'll get y equals 0 plus 1. And we'll just end up with y equals 1, which creates the point 0, 1. Okay. And now what we should do in step 2 is just recognize the inequality. So when it's not even step 2, I'm just going to circle this inequality. It's greater than, so if you remember from the above, greater than means we are going to have a dashed line. So when we graph this, it will be a dashed line. Okay, so that means let's go ahead and graph this. And for the line, and I think even on your MyMathLab homework, all you need to do is pick 2 points. 2 points will graph the line. And right above, we have the 2 points. We have the X-intercept and we have the Y-intercept. So I'm going to graph the X-intercept. I'll just keep this all blue at negative 1, 0, which is right here. Oops. And then I'm going to put the Y-intercept, which is at 0, 1. There we go. And once you pick those 2 points, MyMathLab will automatically draw the line for you. Okay, so now what we're going to do is finish off the rest of the line, and it's going to be dashed because the inequality is just a less than or greater than. So just to complete the rest of this, just draw a dashed line going up and to the right, and down and to the left. Okay.
You say as a boundary graph equal or greater or equal to is a solid line.
Exactly.
But then how do you tell the difference between that and a normal graph line?
So for these, I mean, they're called linear inequalities. So they're always going to be giving us an inequality. So if you ever given greater than or equal to, it's a solid line. And if you're ever given less than or greater than, it's always dashed. The reason we set it equal to in step 1 is just to solve for the X-intercept and Y-intercept.
But we'll never like see a graph with a solid line and need to know if it's greater than or equal to. Or...
Exactly. So let's just say like the equation was just like when we started was just like y equals x plus 2. That's going to be a solid line because this has nothing to do with inequalities. Make sense?
Yes, sir.
Okay, cool. So step 2 was to graph. I'll just say that. This was step 2. Graph. I'll keep that off there though. Step 2, graph. And now step 3 is we are going to pick test points. So since this is an equality, we want to know which side of the graph to shade. So we need to pick test points to see which side of the graph holds true. So step 3, we do test points. And when I say test points, you can pick anything anywhere above the line or anywhere below the line, as long as it's not on the line. So somebody give me a test point. And the easiest one could be what? How about 0, 0? 0, 0 is my test point. Is that below the line?
Yes, sir.
There you go. Okay. So now what we're going to do is take this test point and plug it into the function above that we were given. We're going to plug it into the linear inequality above. So I'm just going to rewrite the linear inequality, y greater than x plus 1. And all I'm going to do here is plug in 0 for y and 0 for x. And let's see what the inequality is going to tell us. So I'm going to get 0 greater than 0 plus 1. And we're going to get 0 greater than 1. Now, is that a true statement?
No.
No, this is false. So this means that whatever point we pick below this line will also be false, which means that we will shade on the opposite side. So what that means is that since all these points will be false, if we pick any of these points, they will be true, which means all we have to do is shade up. That's it. That's what we're doing today. And if you want to see how it holds true, well, pick a point above the line. A good point to pick, I would say, would be 0, 2. Plug it into the equation above. I'll have 2 greater than 0 plus 1, and that'll give me 2 greater than 1, which is true, which means we shaded on the correct side. Okay, so that's what we do for these. Find the x and y-intercept, draw the graph, make sure to note whether it's solid or dashed, and then pick test points and shade. Any questions on this problem? All right, cool. And if, again, you just joined us, here are the notes again. Boom. 5-1, 5-2. There we go. Whoops, who'd that go to? Directly to that person. Sorry. There we go. I'll try it again. 5-1, 5-2. There we go. Cool. Okay, let's keep moving then. So next one is 2x minus 5y less than or equal to 10. So let's go ahead and handle this. Step 1, make it 2x minus 5y equal to 10. 2x minus 5y equal to 10. And find your x-intercept, find your y-intercept. So x-intercept is y equals 0. And then you'll get 2x, whoops, all right, 2x minus 5 times 0 equal to 10. And then you'll get 2x equals 10, and x will equal 5. This will give you the point 5, 0. There's my X-intercept and then my Y-intercept. You let X equal 0. And using the same equation, you have 2 times 0 minus 5y equal to 10. You get just negative 5y equal to 10. Divide by negative 5, and y will equal negative 2. So we have our X and Y intercept. All right. The next thing to note is the inequality. We have a less than or equal to. This means that our line will be solid.
Does the less than mean that it's always going to shade to the right and down?
Oh, it depends on the test point, right? So the less than could be maybe to the right or maybe to the left. So that's the only way. The only way to figure that out is by choosing a test point.
Cool.
Okay. So we have that, which means we can move on to the next step of graphing. And all we have to plot are the X and Y intercept. There we go. Okay. Let's have some fun colors. Yay. All right. So I plot the X-intercept at 5, 0. 1, 2, 3, 4, 5. Right there. I can make that a little bigger. Yeah. 1, 2, 3, 4, 5. And then I plot the Y-intercept at 0, negative 2. Right there. And just like we said, connect the 2 points and our line will be solid. So we would look something, if I have it correct, something like this. Out that way. Yeehaw. Fun colors. There we go. There's our line. Okay. So the last part is to pick test points. So 3 test points. And just like the last one, you're going to pick a test point above the line, or you're going to pick a test point below the line. And what looks like the easiest point to pick again?
0, 0.
0, 0. It's right there. Is that not above the line? There's our test point. Now plug it into the inequality that we were given above. 2x minus 5y less than or equal to 10. So again, I'll just rewrite the inequality. 2x minus 5y less than or equal to 10, and plug in 0 for both x and y. 2 times 0, 5 times 0, less than or equal to 10. And then you'll get 0 less than or equal to 10. Is that a true statement or not?
Yes, sir.
That is true, which means we'll shade which way?
To the left or up?
Or up. There you go. So we're going to shade up towards the point we have picked. There you go. Not bad. Any questions on that, guys?
No, sir.
All right. Okay, let's keep going then. All right. So now, example 3, graph each inequality subject to the non-negative restrictions. And once again, the easiest ways to plot these is to find the x-intercepts and y-intercepts. Okay, so we'll start with the first equation. I'll rewrite it right here. 24x plus 30y greater than 7,200. Okay, 24x plus 30y greater than 7,200. So step one for this is to find your X and Y intercepts. So all I'm going to do is make this as 24X plus 30Y equal to 7,200. And then let's go X-intercept, Y-intercept. So for our X-intercept, again, you let Y equal 0. You'll get 24X equal to 7,200. Since we're plugging in 0 for Y, we already know that that's going to become 0. So all you have to do is write the 24. And now we divide by 24. And that's going to give me 300. So my X-intercept is 300, 0. And then Y-intercept, you let X equal 0, and that's going to give us 30Y equal to 7,200. Divide by 30, and we get Y equals 240. Which gives me the X-intercept of 0 and 240. Okay, we have the information we need from the first equation, and now we have to deal with the next two equations. Well, actually, before we move on, let's just make a note that this line will be dashed. Okay, now we can move on to the other equations. And for X, greater than or equal to 0, well, again, all we have to do is change it into X equals 0. And when we learned from, I think it was 1.2, X equals 0 is the graph of a vertical line. And since this is a greater than or equal to, this line will be solid. Okay. And then the next one is Y greater than or equal to 0, which we change into Y equals 0. And again, from 1.2, this is the graph of a horizontal line. And since this is greater than or equal to, this one will also be solid. Okay. So we have all the information we need from all three of these lines. Any questions on those?
No, sir.
All right. Just you and me today, Charles. Sounds good. All right.
As long as I understand it.
There you go. Okay. So let's go ahead and plot this. And I'll plot the first function. Oh, actually, we need to make our intervals appropriate because we have 300 and we have 240. Okay. So if I make my intervals appropriate, if I have 300, this is going to be 0. I'll make this 100, 200, 300, 400, and 500. And then my Y value is at 240. So could we go by 60s? Would that be good? I think that's fine. You could even go by 80s if you wanted. Let's go by 60s. Let me see. Let's see, there's 60, 120, 180, 240. That'll be perfect. this would be 60, 120, 180, 240, and 300. Okay, perfect. And now I can plot my first function. The x-intercept's at 300 and 0. So that's going to be right here. And then the next function is, or the next point is at 0 and 240, right there. So our line will go down between these 2 points, and it's dashed, right? Yeah. See if I can line that up perfectly. Okay, so there's our dash line. And then we have to graph the other lines. X equals 0, so that's a vertical line. And all this is going to do, and I'll just do this in, I could do it in blue, why not? Come on, computer. Ooh. All right, so all this is going to do is create a vertical line at x equals 0 going down the y-axis. So this is x equals 0. And then the next line to draw is y equals 0, which is going to create a horizontal line going down the x-axis. So it's going to go just like that. And this one's y equals 0. And they're both solid. Okay, so there we go. That was step 2, graph, right? So step 2, graph. Okay, and the next thing we're going to do is pick test points. So I wouldn't worry too much about the lines x equals 0 and y equals 0. Only focus on the actual line we have drawn here for the inequality. And go ahead and pick a point above or below it. And since it's just you and I, Charles, guess what point's going to work out here?
0, 0.
0, 0. This point right here, because that's below our line, right?
Yes, sir.
So we're going to pick 0, 0. And I'll rewrite the inequality again. 24x plus 30y greater than 7,200. And if we plug in 0, 0, you'll get 24 times 0 plus 30 times 0 greater than 7,200. And you get 0 greater than 7,200. Is that a true statement?
No, sir.
That is false. So which way are we going to shade?
Up.
Up. Good. So all our shadings are going to go up. All right. Okay. And also the top of this problem said non-negative restrictions right here. So the non-negative restrictions are known as x greater than 0, y greater than 0, because those restrictions will not allow us to have any negative numbers. So what these restrictions do is they only keep us to the actual first quadrant, because in the first quadrant, everything is positive and everything is greater than 0. So that's why those are called non-negative restrictions. They keep us in the first quadrant. Okay, perfect. All right, everybody good with that one?
Yep.
Okay.
Let's
Then.
hope.
Yep. Let's keep going. All right, now we get to the word problems. Okay. Example 4. Labor costs for a farmer are $55 per acre for corn and $45 per acre for soybeans. How many acres of each crop should the farmer plant if he wants to spend no more than $5,000 on seed? Express your answer as a linear inequality with the appropriate non-negative restrictions and draw its graph. Okay, so here we're gonna have to create our own linear inequality. So for number 4, our inequality, let's call corn, we're gonna make that X. So we're gonna say 55X plus and 45 per acre of soybean, we're gonna call that 45Y. And to finish off this linear inequality, we wanna spend no more than $5,000 on seed. So if you look above, I have translating English into algebra, and no more than is going to mean we're going to use the inequality less than or equal to 5,000. No more than $5,000 on seed. That makes sense?
Mm-hmm.
Okay. And now this wants the non-negative restrictions. So our non-negative restrictions are going to be the same ones that we saw in the above problem. Non-negative restrictions means that all values of X will be greater than or equal to 0, and all values of Y will be greater than or equal to 0. So these are called the non-negative restrictions. Okay, so all we have to do now is solve our linear inequality by finding the X and Y intercept and graphing it and picking a test point, of course. So go through this. Actually, I'll say 1. We're going to change this to 55X plus 45Y equal to 5,000. And then X-intercept, you let Y equal 0. And we get 55X equals 5,000. Divide by 55. And we get 90.909090. So we're going to say 91. We're just going to round it. So X is 90.9, but I'm just going to make this 91. So this becomes 91 and 0. Okay. And then we want the Y-intercept. So we let X equal 0, and we get 45Y equal to 5,000. Divide by 45, and we get Y equals 111.11. So let's just make that 111, which gives us the point 0.111. Okay. Oh yeah, one thing we have to make note of again is that by this inequality, we are going to be solid. Okay. We're ready to graph because we already know what these non-negative restrictions are going to give us. It's going to give us a vertical line and a horizontal line. But we have to make our intervals appropriate. Since X is 90, and Y is 111, let's see what we can do here. I think on the X-axis, I can just go by tens. So 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then my Y value is 111. So I can't go by tens, but I can go by 20s. That might do it for us. So let's just do 20, 40, 60, 80, 100, and 120. Okay. So we make our intervals appropriate, and now we're ready to graph. I'll plot my X-intercept and Y-intercept. X-intercept's at 91, so that's going right there. Oops, somewhere right there. And then Y-intercept is 0 and 111. So I'm just going to put that right between 100 and 120. Right there. And our line is solid, so we'll just connect as straight as we can be. All right, I'm going to try this one more time. Let's do this. Okay, and then draw your non-negative restrictions. So again, we're going to have that line x equals 0. Here's x equals 0. And then we'll have the line y equals 0. Okay, and there's our graph. Everything was solid. Everything is graphed. Let me just put those back to size. And then over here, I'm going to put the X-intercepts. Just to mark them again. 91 was around there. And the other point was around there. 110. There we go. Okay. Perfect. Everything's graphed. Now we want to pick test points. And once again, just focus on this line. And the easiest test point to pick that's below that line is again
0, 0.
0, 0. Perfect. And we plug it into our inequality above. I'll rewrite it here just to do it. 55x plus 45y less than or equal to 5,000. And then you plug in 0 for both. 55 times 0 plus 45 times 0 less than or equal to 5,000. And we get 0 less than or equal to 5,000. Is that a true statement?
Yes.
Yes. So now when we shade, we actually only have to shade in the first quadrant because those non-negative restrictions keep us in the first quadrant. So our shading is only going to look like this. More shadings, more shadings. There we go. That's it. Oh yeah, and then there was another question in there that said, how many acres of each crop should the farmer plant if he wants to spend no more than 5,000 on seed? Well, that's the X-intercept and the Y-intercept, 91 and 111. So I'll put that down here. 91 acres of corn and 111 acres of soybean. Okay. Any questions on this one? Oh man, it's a lot. Okay, cool. All right, let's keep going then. That was 5.1. Now we're on to 5.2. Yeehaw. Which is no different because now we're still graphing inequalities, but now we have 2 or more inequalities. All right. Okay. So we get a system of linear inequalities in 2 variables. So graph each linear inequality using the steps that we just did. But then we're going to have to find their points of intersection, which are going to be called corner points. And then we're going to shade the set of points that satisfy all the inequalities simultaneously. The shaded region is called the solution region or feasible region. Okay. If a region can be completely enclosed in a circle, it is bounded. A region, if you cannot enclose it in a circle, it is said to be unbounded. Okay. So again, now we have more than one equation. We're going to find where these equations intersect. We're going to shade, and we're going to see if we have a solution region, a bounded solution region, or an unbounded solution region. Okay, so let's get started using the same methods as before. So I'll pull the first equation out. Oh, whoops. Didn't change that. Okay. So I'll pull the first equation out. Better stop it, laptop. And make it 3x plus 4y equal to 12. And just like before, solve for your x-intercept, y-intercept. This method couldn't be any more repetitive. X-intercept, you let y equals 0, and you'll get 4y equals 12. Whoops, nope, the other way. 3x equals 12. Divide by 3, and x will equal 4. This creates the point for 0. Okay. And then the y-intercept, we let x equal 0, and we'll get 4y equal to 12, and y is going to equal 3. We get 0, 3. Okay, that one's done there. Now we'll pull out equation 2. And we'll make it y equal to -3. Now, all we have to understand from this is that y equals -3 is a horizontal line. Okay. And once again, before moving on, these are less than or equal to, greater than or equal to. So both lines are going to be solid. All right. So we have everything figured out for both lines. Let's go ahead and graph them. Zoom, 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 right there. Okay. So for the first line, I have an x-intercept at 4. So 1, 2, 3, 4 right there. And then a y-intercept at 3. 1, 2, 3 right there. And then just connect these lines. And we are solid, right? Nice and steady. So there's the first line. And then my second line is y equals -3. So for that one, let's just use this color. You're going to find -3 on the y-axis and make a horizontal line. 1, 2, 3. So here's y equals -3. Okay. So the next thing we want to find is their point of intersection. We want to know where exactly did they intersect at. So that's going to be this point right here, right where they intersected at. And if you drew your graph perfectly, you know where it's at. Mine is a little off, but if you drew it perfectly, then if you intersected, you should have intersected where? This point. So if y is -3 and I plug that in, you'd get -12 and the 24, so 8. Okay, so 1, 2, 3, 8, -3. Okay, so where they intersect is at 8, -3. This is called a corner point. Okay, but now after you find the corner points, we still need to pick test points. So next is picking test points. And once again, what point happens to be below this line and above this line?
0 and 0.
0, 0. That's it. Our test point is going to be 0, 0. But this time, we have to test it into both functions, not just one. We test it into both. So I'll have 0, 0 of 3x plus 4y greater than or equal to 12. And let's start with this one first. If I plug it in here, you get 3 times 0 plus 4 times 0 less than or equal to 12. And 0 is less than or equal to 12. Is that a true statement?
Yep.
That means we will shade towards the point, which means for the lovely colored function I have up there, we're going to shade down. Okay, but then we still need to put 0, 0 into the second equation. So 0, 0 plugged into y greater than or equal to -3. And you plug in 0 for y, that's all we can do, and you get 0 greater than or equal to -3. Is that a true statement?
Nope.
Sure. Is 0 bigger than -3?
Oh, yeah. Yeah, it is.
So since our test point of 0, 0 is true on both of them, well, now for the orange line, we are going to shade up, directly up. And the part where your shadings intersect is called the feasible region and the solution region. So what we say by that is if we pick any point in this region, it's going to hold a true answer for both equations. But now we have to see that our solution region is unbounded because these solutions go on infinitely. I cannot draw a circle around these because these shadings continue forever, for infinitely. So what we have to say here is that our solution region, I'll say it over here, solution region is unbounded. There we go. Okay. And that's what we're going to be doing on these next examples. Everybody good? All right, next one. Let's do it again. Solve the system graphically and find the coordinates of the corner points and state whether we are bounded or unbounded. Okay. So I'll bring this first equation out. We have it as 3x plus 4y and set it equal to 24. And just like before, X-intercept, Y-intercept. X-intercept, y equals 0. So you'll get 3x equals 24 and x equals 8. Here we get 8, 0. And then Y-intercept, we let x equal 0. And we end up with 4y equal to 24. And y is going to equal 6. Okay. And then for the other equations, I'll say equation 2, x greater than or equal to 0. Once again, that is a non-negative restriction. So we get x equals 0, another vertical line. And the same can be said for the next one. Equation 3, y greater than 0. This is the same as y equal to 0, which is a horizontal line. And now, what can be said for all of these restrictions is that all of these lines will be
Solid.
Solid. Good. Which means let's go ahead and graph. Okay. So we'll plot the first one at 8 and at 6. 1, 2, 3, 4, 5, 6. There we go. And connect. So there's our first one. And then remember the other two are just horizontal and vertical lines. So I'll just do one in orange. I think I left that there. So here we go. Here's x equals 0. And then I'll do that one in purple. Why not? Here is y equals 0. Okay, so after we graph them, we want to find the corner points. Where do these lines intersect each other? So we're going to have an intersection point here on the y-axis. Whoops, I'll zoom in so I can pinpoint them better. So my intersection points are at 0, 0, and then 8, 0, and then 0, 6, right here. So this is, it's big, but it works. 0, 6, 8, 0. Well, maybe I should write smaller. So this is 0, 6, 8, 0. And our last corner point is 0, 0. So these are all the corner points. So I'll list those over here. We have 0, 6, 0, 0, and 8, 0. Okay, cool. Now the last part is test points, of course. My functions, there we go. And since the x greater than 0 and y greater than 0, since they're the non-negative restrictions, we only have to worry about putting test points into the first function. That's it. So we'll say test points. And just look at this function here. And what is a lovely test point below that function?
0, 0.
0, 0. That is our best friend today. Okay, so we plug it in just to the first one, 4y less than or equal to 24. Plug in 0, 0. Everything will become 0. And you'll get 0 less than or equal to 24. Is that a true statement?
Yes, sir.
Yes, which means we're going to shade towards 0, 0, but we're not going to leave the first quadrant. We're just going to stay right here in the first quadrant. Okay, and there's our feasible region, our solution region, and is it bounded? Can I draw a circle around it? That's definitely bounded, right? If I can draw a circle around it, that is called a bounded feasible region or solution region.
So in the situations where it's not bounded, it's because you have infinite solutions in one.
Exactly. Like on the last problem, everything kept going out that way, which means you can't put a circle on it because all those points would be solutions. So it's infinitely many solutions for those, which means it's unbounded. But since we're trapped in the first quadrant, we can bound it, and this is our feasible region. So we can say, if I have room, I'll do it over here. This is our bounded feasible region. Okay. So corner points, X and Y intercepts, graph everything, corner points, I think is only the new thing here, and test points. That's it. Everybody good?
Yes, sir.
Okay. Let's keep moving. Okay. So example 3, same thing. Get these equations, find their X and Y intercepts, plot them, find the corner points. Remember that these are the non-negative restrictions, which keep us in the first quadrant, right? So these are the non-negative restrictions, and they keep us in the first quadrant. So go ahead and try this one out on your own, and I'll be right back because I think the pest control guy's here. So go ahead and try it out. There we go. Okay. I'm back. So let me start doing this one. So 1, 6x plus 3y equals 24. And then X-intercept y equals 0. So 6x would equal 24 and x would be 4, which gives me 4, 0. And then Y-intercept x equals 0. Yeah, that's fine. Yeah. I know it's like non-toxic to children, but yeah, but still, yeah.
That's priority number 1.
Yeah. Appreciate it.
No problem, man. You're good to go.
All right. Awesome.
You want to expand it or you want me to get it from your wife?
Yeah, I left it out there downstairs for her. So yeah, appreciate it, Eddie.
If you need anything else, let me know, man.
Okay, for sure. Okay, so I did that. And then 2. 3x plus 6y equal to 30. And again, X-intercept, Y-intercept. Ten, 0. And then Y-intercept. 6y equals 30. And y is going to be 5. Good. And we get 0, 5. Okay, cool. And then one thing to note again about all of these lines is that they're going to be solid. But I'll just remove that. There we go. Okay, let's graph. 4 and 8. I'll keep these just purple and orange. How about that? So 4 and then 8. Solid. And then that's good. And then 10 and 5. 10 and 1, 2, 5. There we go. Way off. One more time. Whatever. Got it. And then bam, there we go. Okay. There's my 2 lines, a little crooked, but whatever. And then I can draw the non-negative restrictions. So I'll just make that into blue. Here is x equals 0. And then here's y equals 0. Okay, perfect. So what we need to find next is our corner points. So I'll zoom in, And it's where all our lines intersect at. So here's a corner point. Let me make that bigger. Down here. Come on, there we go. Here's a corner point at 0, 0, and then a corner point here, here, and I think just here. And this is where all our lines intersect at. Okay, so these are the corner points that we want. And to label that, I have 0, 0. And then I have 1, 2, 3, 4, 5, 0, 5. And this one is 1, 2, 3. That one's 4, 0. And if you drew your graph really nicely, then this one should be 2 and 4. 2, 4, I believe. Okay, excellent. And the reason I'm not counting these intersection points yet is because when we start shading, so you'll see why. Corner points. So it's going to just be the corner points of the feasible region. I think 2, 4 works. Let me double check. Let's see. That would be 12 and 12. Good. That would be 6 and 24. We're good. Okay. So now we have our corner points, which I'm going to label. And we're going to have 0, 5, 0, 0, 2, 4, and 4, 0. All right. Then next is test points. And just focus on the orange line and the purple line. And guess what point is nice and below both of those?
0, 0.
0, 0. It's lovely, right? Such a great test point. Until a function is actually on 0, 0, like the very first one we did today, we can't choose it. Well, was it? Oh, I don't know. But if it is on there, we can't choose it. Okay. So we're going to plug it into the functions given in the beginning. So I'll start with the first function, 6x plus 3y less than or equal to 24. And you plug in 0 and 0, you'll get 0 less than or equal to 24, which is true. Which means for the purple line, I would start shading down. There we go. And then if we do 0, 0 for the orange line, which is 3x plus 6y, let me write that. So, oops. 0, 0 for 3x plus 6y less than or equal to 30. If you plug 0 in there, you'll get 0 less than or equal to 30, which is also true. Which means for that purple line, we would shade down. I don't want to use purple again, though. I'll just use red. I mean, not for the purple, for the orange line. So we would shade. Actually, no, purple would be good then. So down, 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 down. Okay. And so once again, I don't need the corner points of the outer regions or of the outer sections where they intersect, because right here is the feasible region. So this, I can draw a circle around, and this would be my feasible region or solution region that is bounded.
Just the purple area, right?
Purple and the green, right? Where they intersect. Yeah. Because you could shade everywhere else. Like I can shade, like this purple line could have kept shading downwards. So it could have kept going this way, this way, this way, this way, this way, if you wanted it to, but we don't need to go past the first quadrant because of those non-negative restrictions, right?
But everything, like the green portion that's shaded above the purple portion, those are solutions to all of them?
No. So if it's above the intersection, those are not solutions. So
Yeah, okay.
again, yeah. So maybe I can make that smaller. So right here, like this part is just
Is
my
the-
feasible.
Okay,
That's it.
yeah.
Yeah.
Just making.
There you go. That's my bounded feasible region. Okay. Not bad. Everything's the same, right? Same technique. Okay. Hey, and we made it to the last question of the day. Yeehaw. So another application problem. So this is kind of hard to read, but it says a manufacturing company makes two types of water skis, a trick ski and a slalom ski. The trick ski requires 6 labor hours for fabricating and 1 labor hour for finishing. The slalom ski requires 4 labor hours for fabricating and 1 labor hour for finishing. The maximum labor hours available per day for fabricating and finishing are 108 and 24 respectively. If X is the number of trick skis and Y is the number of slalom skis produced per day, write a system of linear inequalities that indicates the appropriate restraints on X and Y, and find the set of feasible solutions graphically for the number of each type of ski that can be produced. Okay, so X is the trick ski, Y is the slalom ski, and there are 108 hours for fabricating. So the trick ski says that there are 6 labor hours for fabricating, which means that that is going to fill out the first equation of blank X plus blank Y less than or equal to 108. So X represents the trick ski, and the trick ski requires 6 labor hours. And now let's look at the slalom ski, and the slalom ski requires how many hours for fabricating? I think it's 4. And then for finishing total, there are a maximum total of 24 finishing labor hours, and each ski requires 1 labor hour for finishing. So this would be 1x and 1x or 1y. And there you go. Now all we have to do is solve them using the same techniques we've been doing today. So start with the first equation. 1, we have 6x plus 4y, and I'm going to make it equal to 108. And go X-intercept, Y-intercept. I'll leave those, that's fine. And you'd get 6x equals 108. And 108 divided by 6 is 18. So x would be 18. So 18 and 0. And then y-intercept, you let x equals 0, and 4y equals 108, and you divide by 4, and we'd get 27. And this would be the point 0, 27. Okay, So that's the x-intercept and y-intercept for the first equation. Now we look at the second equation. 2. 1x plus 1y equal to 24. And for my x-intercept, you let y equals 0 and x equals 24. That's the point 24 and 0. And then y-intercept, you let x equals 0 and y equals 24. And that gives me 0, 24. All right, that's the information we need. X-intercepts, y-intercepts from both equations. Also take note, all of these lines will be solid. Okay. Let's plot everything we have. So I think we have to make our intervals appropriate. We have 18, 24, and then for the y-axis, we have 27 and 24. So I think we're going to have to go by 3s on the y-axis, and we can go by 6s on the x-axis. Let's see how that works out for us. So this will be 0. Then I can do 6, 12, 18, 24, 30. Why not? So 6, 12, 18, 24, 30. And then for my y values, we're going to go by 3s because there's a 27 in there. So 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. There we go. Now let's plot everything we're given. All right. My first line is going to be purple. So x equals 18. That's going to be a point right there. And then y equals 27, which is up here. So I just connect those. And then the next line is 24 and 24. Good. We'll make that orange. 24 and 24. And then connect those two lines. There we go. And the last pieces to draw are those non-negative restrictions of x greater than or equal to 0 and y greater than or equal to 0. So we already know what type of lines those make. So for x equals 0, we're going to get this vertical line. Here's x equals 0. And then y equals 0 is going to be this horizontal line. And there's y equals 0. Okay, cool. So what we should actually do, let me see, because we can find all the corner points, but let's go ahead and shade first to help us find the solution region to find the corner points. So that means let's just go ahead and pick test points. Okay, so for this one, if I pick test points, baby. That's ugly. Test points. Yeah. There you go. Just focus on the yellow and purple line. And once again, what is the best point to choose here? 0, 0, right? That's right below both of those lines. Okay, so we'll look at the first function, 6x plus 4y less than or equal to 108. Plug in zeros for the x's and y's, and you'll get 0 less than or equal to 108. That is a true statement. So we are going to shade down on the purple line. Let me zoom in for that. Down. So again, we don't need to go past the first quadrant. Okay. And then put 0, 0 into the second equation. I'll do, what's a good color to shade down with? Red. So we'll have 0, 0 into x plus y less than or equal to 24. And we get 0 less than or equal to 24, which is again true, which means we're going to shade down on the orange line now. So shade down, 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 down. There we go. And now we can see where all our shadings intersect. So we can see the corner points of our solution region. So the corner points are going to be at 0, 0, 18, 0, 20, 0, 24, and whatever this intersection point is. Those are the only corner points we need to find. So we have 0, 0. We have 0, 24. We have 0, 18. Not 0, 18. 18 and 0. And now we need to figure out what that one is. If we drew it correctly, that should be 3 and 21, maybe. Let's see how true that is. Is that 3 and 21? If I have 6 times 3 plus 4 times 21, oh, I get 102. So no, it may not be that. Okay, so one of the ways to find this corner point, since 3 and 21 is not correct, is going to be by either using a system of equations, or we can use Desmos and find out where these functions intersect. Watch this. We're going to save a lot of time here. Not now, Desmos. Close you. And then what I'm going to do here is put these equations, 6x plus 4y equal to 108, and x plus y equal to 24. And now watch this magic. It's going to give me that exact intersection point. All I have to do is click on it. Bam. 6 and 18. I was way off, right? 6 and 18. So this one is 6 and 18. And there's our corner points. Desmos to save the day, right?
Oh yeah. Less steps is good.
Yep. Okay, so those are our corner points. We can label them, and we know our solution region. So, I mean, I'll just leave those there. We know those are our corner points, and if I zoom in, here's our solution region. What's a good color? I can use this one. Yeah, funky. That is our bounded solution region. Okay. I guess Dan, it says find the set of feasible solutions graphically for the number of each type of ski that can be produced. Okay. Well, I would assume the most feasible boundary point would be that 6 and 18, right? Because you don't want to make 0 and 0 skis. You don't want to make 18 of one ski, and you don't want to make 24 of one ski. So 6 and 18 would be the most feasible solution. That works. Okay. I'll just write that down here. And that's it. That is 5-1 and 5-2. Any questions on these notes?
No, sir.
Thanks for hanging out, Charles.
Yes, sir.